In 1945, near the coast of Japan, an American F4U Corsair fighter plane crashed into the sea after its engine failed during a mission. As the aircraft hit the cold Pacific waters, the pilot managed to eject. Within hours, Japanese patrol boats reached the wreckage. What they recovered would turn out to be one of the most valuable pieces of intelligence in the final months of the war. For almost 3 years, Japanese pilots had faced this American fighter over the skis of the Solomon Islands, Rabaul, the Philippines, and now above their home islands. They had learned to respect its incredible speed, heavy firepower, and nearly indestructible build. But never before had they captured one intact, a chance to study, measure, and truly understand how far behind they were. The story of Japan's encounter with the F4U Corsair is not just about a captured airplane. It's about a nation's awakening to the reality of American industrial and engineering power. Through examining this fighter, Japanese engineers discovered shocking truths about production precision, material science, and design philosophy, lessons that shattered their previous assumptions about their own capabilities. The Corsair that Japan recovered represented the peak of American fighter development. Designed in 1938 to meet the U.S. Navy's tough requirements, the F4U had evolved from a bold experiment into one of the most feared aircraft of the war. Its distinctive inverted gull wings, massive Pratt & Whitney R2-800 double Wasp engine, and revolutionary performance made it instantly recognizable. Most importantly, the Corsair achieved what Japanese aircraft designers struggled with: a perfect balance of speed, firepower, range, and structural strength. The Corsair's story began in 1938, when the U.S. Navy's Bureau of Aeronautics issued a request for a fighter that could exceed 400 miles per hour, an extraordinary demand at the time, since most fighters barely reached 350 mph. But the Navy didn't want just speed. It needed an all-around machine: low stalling speed for carrier landings, a 1,000-mile range, strong armor, and the ability to carry bombs. The Chance Vought Company responded with a daring design. Chief designer Rex Beisel and his team decided to build their aircraft around the most powerful engine available, the 18-cylinder Pratt & Whitney R2-800 double Wasp, producing 2,000 horsepower, almost twice that of other fighters. To harness that power, they added an enormous 13-foot 4-inch propeller, the largest ever fitted to a fighter at the time. But this created a serious challenge: how to keep enough ground clearance for such a big propeller while maintaining a short, strong landing gear suitable for carrier operations. The solution became the Corsair's trademark: its inverted gull wing design. Instead of straight wings, Beisel's team angled them downward from the fuselage before leveling them out, forming a distinct M shape when viewed from the front. This gave the propeller enough clearance while allowing for shorter landing gear and better aerodynamics. The prototype, XF4U-1, first flew on May 29, 1940, piloted by Vaught's chief test pilot, Lyman A. Bullard Jr., at the factory airfield in Stratford, Connecticut. On October 1, 1940, during a test flight between Stratford and Hartford, the XF4U-1 reached a ground speed of 405 miles per hour with a tailwind, making it the first American single-engine fighter to break the 400 mph barrier. Its true level flight top speed was 378 mph at 23,500 feet, an outstanding performance for 1940. By late 1942, production F4U-1 Corsairs began arriving at combat units. The first squadron to receive them was Marine Fighter Squadron VMF-124, which deployed to Henderson Field on Guadalcanal on February 12, 1943. The Corsair's combat debut, however, was rocky. On February 14, 1943, Valentine's Day, during what became known as the St. Valentine's Day Massacre, 2 Corsairs, along with several P-38 Lightnings, P-40 Warhawks, and bombers, were lost in a disastrous engagement. The Japanese defenders lost only 1 fighter. The 9-to-1 loss ratio was so devastating that all American daylight bombing missions over Bougainville were temporarily suspended, while tactics were reevaluated. This battle proved that advanced technology alone cannot guarantee victory. Strategy, experience, and the right use of tactics were just as important. American pilots quickly adapted. They learned that the Corsair's true strength wasn't in tight dogfights, but in what became known as boom and zoom tactics. The Corsair couldn't outturn a Japanese Zero in slow-speed maneuvers, but it could outclimb, outrun, and outdive any Japanese fighter. Success depended on keeping the advantage of speed and altitude, diving down on the enemy, firing, and then using that superior speed to break away before the opponent could react. On May 13, 1943, Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace by mastering these tactics. He would go on to achieve 21 aerial victories. As the war continued through 1943 and 1944, the Corsair's reputation grew stronger. Marine squadrons flying from hastily built coral airstrips across the Solomon Islands used the aircraft's toughness to devastating effect. The Corsair could take damage that would have destroyed lighter Japanese planes. Armed with 6.50 caliber Browning machine guns, 4 inner guns carrying 400 rounds each and 2 outer guns carrying 375 rounds each, it could fire a total of 2,350 rounds, giving it unmatched firepower. Later versions, like the F4U replaced the machine guns with 420 cannons, though many pilots still preferred the reliability and high ammo capacity of the .50 caliber. The Corsair was also incredibly versatile. By mid-1944, it was regularly carrying bombs and rockets on missions. It could mount 1,000-pound bombs, 5-inch rockets, or napalm canisters on its centerline and wing racks. This gave it a powerful ground attack role, making it a vital asset for close air support during amphibious invasions. During the 1945 Battle of Okinawa, Corsairs flew thousands of ground attack missions, earning the nickname the Angels of Okinawa from grateful infantry troops. From the cockpit of a Zero or another Japanese fighter, pilots saw the Corsair as a terrifying opponent, faster, stronger, and far more durable. But to truly understand what made it superior, Japan needed to study the captured plane up close. That required careful technical analysis. Japan had 2 key facilities for such research: the Yokosuka Naval Air Technical Arsenal, south of Tokyo, the Army Aviation Technical Research Institute at Takekawa. Throughout the war, these institutions examined captured Allied aircraft, recovering parts and wrecks from battlefields across the Pacific. Their studies gave Japan valuable intelligence about American technology, but most aircraft they obtained were damaged or incomplete. So when they recovered a nearly intact Corsair, it was an extraordinary opportunity. The Yokosuka facility had been conducting aviation research since April 1, 1932, when it was reorganized as the Kaigun Kokusho Naval Air Arsenal. During World War II, it employed thousands of engineers, designers, and technicians. The arsenal was responsible for designing many Japanese naval aircraft, although production was handled by companies like Eichi, Nakajima, and Mitsubishi. By 1945, the engineers at Yokosuka were highly experienced and understood advanced aircraft design at the highest level. So when the recovered Corsair arrived there early that year, it represented one of the most modern American fighters they had ever seen, and in surprisingly good condition. Although the plane had suffered some water damage during its forced landing, the main structure remained intact. Salvage teams worked quickly to prevent it from sinking completely and transported it safely to Yokosuka's secure testing area for detailed examination. Their first step was to assess the overall condition. Despite being submerged in salt water, most of the Corsair's components were undamaged. The massive Pratt & Whitney engine required complete disassembly and cleaning, but the airframe showed no combat damage, a critical detail. In previous cases, Japan had only managed to recover heavily damaged Allied planes, making it difficult to tell which features were due to combat and which were part of the design. This Corsair gave them a rare, clear look at American engineering. Japanese experts began by carefully photographing and measuring everything. Every dimension was recorded. Wingspan, 40 feet 11.7 inches. Length, 33 feet 4 inches. Height, 15 feet with wings extended, or 16 feet 2.3 inches when folded for carrier storage. The inverted gull wing design immediately caught their attention. The engineers understood the aerodynamic and structural advantages of this shape, but they also recognized how complex and costly it must have been to manufacture. Most Japanese factories at that stage of the war simply did not have the advanced tools and strict quality control needed to produce complex curved parts and hold precise angles reliably. The Corsair test revealed several things that surprised the Japanese technical team. Even though the Corsair was an advanced airplane, some outer wing surfaces were covered with fabric instead of metal. Fabric also covered control surfaces like ailerons, flaps, and the rudder behind the main wing spar and the armament bay. At first, Japanese experts found this odd. By 1944-45, most modern fighters used all-metal skins. Further studies showed the fabric was a deliberate design choice from the plane's 1938-40 development. It saved weight where the structure carried little load and left aluminum for the critical, load-bearing parts. The treated fabric, when correctly applied, provided enough strength and weather protection for much less weight than metal skin. This showed a mature understanding of how to allocate materials for best performance. When the Japanese dismantled the wing structure, they found workmanship that was both impressive and frustrating. The main wing spar, the critical structural member that carries flight loads, was a huge forging made of a high-strength aluminum alloy. Japanese shops struggled to match the material properties and size of that forging. The spar's dimensions and load capacity exceeded anything found in contemporary Japanese fighters. That single part highlighted a fundamental difference. American industry could produce large, complex forgings to consistent standards, while Japanese manufacturers increasingly relied on built-up assemblies made from many smaller parts. Inside the wing, stamped ribs made from aluminum sheet showed notable precision and uniformity. Each rib was nearly identical to the next, a sign of tight quality control in the production process. By contrast, Japanese aircraft production was showing more variation in the quality of individual parts as the war went on. Inspectors also examined the Corsair's guns. The 6 Browning .50 caliber machine guns mounted in the wings represented overwhelming firepower. But what impressed the Japanese even more was not just the guns themselves, but the completeness of the whole system. Ammo boxes, feed mechanisms, spent case ejection, and the reloading and charging systems were all engineered to work smoothly together. The guns were examples of precise manufacturing, and American ordnance production had achieved a level of reliability that Japanese industry could only envy. The Browning M2 design, after decades of refinement, was produced in huge numbers with remarkable consistency. The Japanese technicians recognized that these weapons reflected manufacturing techniques and quality, standards their own factories could not match reliably. They also noticed the protective design features around the cockpit, a 150-pound armor plate, and a 1.5-inch thick bulletproof glass panel behind the windscreen, which underlined an American design philosophy that accepted some extra weight to improve pilot survival. Japanese fighters had generally favored lighter weight and higher performance over heavy armor, which had worked early in the war. But as American fighters became faster and more heavily armed, the lack of protection became deadly. The Corsair showed that you could include effective armor without sacrificing performance, thanks largely to the enormous power of its engine. That engine, the Pratt & Whitney R2800 Double Wasp, represented the peak of American aero-engine development at the time. It was an 18-cylinder radial arranged in 2 rows of 9, displacing about 2,800 cubic inches and producing over 2,000 horsepower. It was a mechanical masterpiece. Japanese engineers had seen this engine on captured planes before, but never in such good condition for careful study. Its construction and the production capability behind it seemed almost unbelievable. Cylinders and parts were machined to tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine builders struggled to achieve. The engine also used a 2-stage supercharger system to keep power at high altitude, with complex internal air passages and precisely mounted rotating parts, all signs of advanced design and very high manufacturing skill. Because of production limitations, Japan's attempts to develop a similar supercharger system mostly failed. Perhaps the most impressive thing about the Corsair's engine was its reliability and power. American radial engines could run for hundreds of hours between overhauls while still producing their rated horsepower. Japanese engines, even new ones, often failed to reach their theoretical power output and needed frequent maintenance. The R2800's consistent performance came from better metallurgy, higher quality lubricants, more precise manufacturing, and stricter quality control. The propeller system was equally impressive. The 13-foot, 4-inch Hamilton standard hydraulic propeller, with its variable pitch blades, showed advanced aerodynamic design and hydraulic engineering. Japanese engineers understood propeller theory, but they lacked the factories capable of producing such large, precise components. Tests across the aircraft revealed a consistent pattern. The landing gear system was complex but carefully built. The cockpit instrument panel had far more gauges and controls than any Japanese fighter. The fuel system included self-sealing tanks, made from layered rubber compounds that swelled when punctured to prevent leaks, a feature missing in most Japanese planes. The electrical system powered many devices through well-organized, properly insulated, high-quality wiring. Most striking of all was the overall quality of materials and manufacturing. Every part from major structures to small fasteners showed the same high standard. The aluminum alloys had uniform properties, the steels were properly heat-treated, and surface finishes were smooth and professional. The Corsair felt solid, well-built, and designed to last. By contrast, Japanese aircraft built in 1945 were of far lower quality. Wartime shortages forced the use of substitute materials, aluminum quality declined, and many skilled workers were drafted into the military. Factories operated under constant threat of American bombing, and with production deadlines emphasizing quantity over quality, quality control suffered badly. The captured Corsair was tested when Japan was already facing certain defeat. American B-29 bombers were systematically destroying Japanese cities. The Navy had collapsed at Leyte Gulf. The Philippines were lost, Iwo Jima had fallen, and Okinawa was under attack. In this desperate situation, the Corsair test was no longer about gaining intelligence for future victories. It was a final, honest look at reality. Japanese engineers at Yokosuka and Takekawa documented their findings in detailed technical reports. They recorded precise measurements, described manufacturing methods, and evaluated American capabilities. Though the reports sounded professional, they couldn't hide the truth. America's technology surpassed Japan's in almost every area. The gap was not small, nor was it something Japan could easily close. It reflected years of industrial development, massive investments in research and machinery, advanced supply chains, and access to resources Japan simply didn't have. By August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests that technicians managed to repair at least one enough to make it airworthy. Photos show Corsairs with patched wings and fuselages. It's uncertain whether any actual flight tests occurred, but the repair work shows a serious effort to get the aircraft operational for study. When American occupation forces arrived at the Yokosuka Naval Air Technical Arsenal in September 1945, they found extensive evidence of Japan's intelligence work. Captured Allied planes were scattered around the facility. Technical reports, drawings, and photographs revealed Japan's attempts to understand Allied technology. U.S. intelligence officers collected these materials, recognizing their value and showing how much Japan had learned. The story of Japan's examination of the F4U Corsair represents more than just technical intelligence. It symbolizes the enormous technological gulf between American and Japanese aviation at the end of the war. In early 1943, when the Corsair first entered combat, Japanese Zero pilots could still compete effectively through superior tactics and flying skill. But by 1945, even Japan's most experienced pilots in their latest aircraft stood little chance against a well-flown Corsair. The Corsair's advanced technology, combined with America's overwhelming numbers and superior pilot training, created impossible odds for Japan. The Corsair achieved an official kill ratio of 11-1 against Japanese aircraft. During World War II, American pilots flying the Corsair shot down 2,140 Japanese planes, while losing only 189 Corsairs to enemy action. These numbers reflected not only the Corsair's technical superiority, but also the overall strength of the American war machine. Better training, stronger logistics, unmatched industrial power, and advanced technology at every level. The Japanese engineers who studied the captured Corsair understood all of this. They could measure the performance gap, analyze the production differences, and calculate the disparity in resources. Their reports, filled with data and observations, became a quiet acknowledgement of Japan's industrial struggle against America's might. The Corsair itself continued to serve long after World War II ended. It fought in the Korean War, 1950–1953, where it proved highly effective in ground attack and close air support missions, even as jet fighters began to take over air superiority roles. Foreign air forces, including France, flew Corsairs into the 1960s during colonial conflicts. The Corsair's final combat mission came in July 1969, during the brief football war between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto shot down 3 Salvadoran aircraft, 2 of which were also Corsairs, marking the last air victories ever achieved by the type. From its first flight in 1940 to its final combat nearly 30 years later, the Corsair proved to be one of the most successful and long-lived fighter aircraft designs in history. For Japan, encountering the Corsair during the U.S. occupation became part of a larger reckoning with technological reality. Japanese engineers and scientists who had struggled through wartime shortages and industrial limits now worked alongside American occupation authorities to rebuild their nation's industry. The lessons learned from examining American technology, including the Corsair, deeply influenced Japan's post-war industrial philosophy. The emphasis on quality, precision manufacturing, and continuous improvement, which would later define modern Japanese industry, had its roots in the hard lessons learned when Japanese engineers studied what American industry was capable of producing. The Corsair, recovered in early 1945, represented more than a crashed fighter. It symbolized the engineering excellence and manufacturing sophistication that Japan had sought throughout the war. The lessons it offered came too late to change the outcome of the conflict, but they helped shape the peace that followed. While testing this American warplane, Japanese engineers came face to face with the full extent of the challenges their country faced. They had fought with courage and skill, but bravery and talent alone could not overcome their enemy's vast technological and industrial advantage. The story doesn't end with victory, it ends with understanding. The Japanese technical reports on the Corsair, discovered later by American occupation forces and now preserved in archives, stand as silent witnesses to a moment when one nation's engineers confronted the capabilities of another. The Corsair they examined is long gone, likely dismantled in the chaos of the post-war years, but its legacy lives on in the lessons it taught. What can be achieved when technology, resources, and craftsmanship come together in perfect harmony? In the post-war era, Japanese aviation would rise again, but never again would Japanese engineers underestimate what their American counterparts could achieve when given the industry, science, and freedom to realize their designs fully. The Japanese examination of the F4U Corsair in 1945 marked a turning point, a moment when Japan's aviation community finally understood the deep technological gap that had opened during the war. It was a lesson not written in propaganda or battle reports, but in aluminum alloys, precision fittings, and manufacturing tolerances, speaking louder than any words about the true power of American industry.